In section 8.4, we're going to look at how to find partial derivatives algebraically. How do we actually incorporate our derivative rules that we learned in Calculus 1 to these functions of two variables? So again, to emphasize, we're not doing new derivatives. We don't have new derivative rules, but rather our new thing is about how do we take a function of two variables and how do we think about it as a function of one variable with a cross section in some way. So here's the idea. If we want f sub x, that is the partial derivative with respect to x, we will think about y as a constant and then take a normal derivative. So we're going to think about y being just some number like 2 and then take the derivative with respect to that. And if we want f sub y, the partial with respect to y, we're going to think about x as a constant. That's the new thing. All the derivative rules that we're going to do are the exact same that we learned in Calc 1. The power rule, product, chain, quotient, all of those are the exact same thing. So the other new thing is that we have two partial derivatives to do for any function, not just one derivative. So example 1, find the two partial derivatives of f of xy being 2xy plus 3x plus 4y squared. So first, let's look at the partial with respect to x. We're going to look at the derivatives of each of those three parts, the 2xy, the 3x, and the 4y squared. And again, we're going to think about y is a constant here. So this is going to be equal to the derivative of 2xy plus the derivative of 3x plus the derivative of 4y squared. And we can just do these derivatives just straight out, but we're going to have the added notation that this y is a constant. So, for instance, this 4y squared, that is just going to be one big constant. And we know that the derivative of a constant is just 0. So this whole last term is 0. This derivative of 3x with respect to x is just a normal derivative. So that's just going to give us the derivative of 3x, which is 3. And then if we're mixing the x's into y's, that gets a little more complicated. Maybe it makes more sense to think about 2xy as 2 times y times x. This is a constant times x. And note that that is really going to act as the same thing as this 3 times x. When we did that derivative, we just took the constant as the derivative, and we're going to do the same thing here. 2y is the derivative of 2yx with respect to x. And again, 2y is a constant. We did the derivative of 3x in the exact same way. It's just now given in terms of y. So put it all together. Our derivative is 2y plus 3. We're going to go through these first examples slowly. It takes some getting used to think about y as a constant, and kind of, it seems maybe a little bit awkward of having the partial with respect to x have y in it, but that's going to happen often. And again, it's thinking about it as a constant and just keeping it through the whole problem. All right, let's do the same thing now. F of y, this time now, x is a constant. So this is going to be the derivative with respect to y, 2yx, plus the derivative with respect to y of 3x, plus the derivative with respect to y of 4y squared. And I'm going to rewrite this 2yx how we had before, 2xy, so we can do the kind of the same constant idea as before. So let's label all of our constants. This 2x is a constant. this 3x is a constant, and if you want, this 4 is a constant. The derivative of 4y squared is just normal. That's just going to be an 8y using our power rule. The derivative of a constant is always 0, so we're going to get nothing out of that because there's no y in that derivative. And then similarly as before, the derivative of 2xy is just going to be y times some constant, and the derivative there is going to be just 2x. So putting it all together, we have the partial with respect to y is 2x plus 8y. This is a process that takes a little bit of getting used to, but as you do a few examples, you'll get more and more used to this idea of setting one of the variables equal to a constant and then just taking normal derivatives past that. All right, the other complication we're going to have is we're going to be looking at second derivatives of functions of two variables as well. Remember, in calculus 1, we think about the second derivative tells us something about the concavity of the function. What's the curve going to look like? And the second derivative will give us an analogous kind of idea of the curve. And we're going to use this in the next section, 8.5, when we think about mins and maxes of a function. So we can use this little chart to think about the derivatives. And again, there are 4 second order partial derivatives given like this. So here, if we start with our function and we take the derivative with respect to x, we get f sub x of xy. If we take the derivative with respect to x again, we get f sub x of xy. So that's the same thing as this function taking the derivative with respect to x. We just write the notation without the parentheses. On the other hand, with that function of f of x, xy, we could have taken the derivative with respect to y. So that would be this new function, this new partial, taking its derivative with respect to y instead of x. As every function, you have 2 options on the partials that you're going to take. And of course, at the very beginning, we could have taken the derivative with respect to y as well. And again, we could have taken the derivative with respect to y again. So that would be our partial f sub y with respect to y again. Or we had the choice of taking the derivative with respect to x, which would have given us f sub y with respect to x. So each derivative, you have 2 options, which derivative you take it with respect to, which variable, which means that you have 2 first-order partial derivatives, 4 second-order partial derivatives, and if we continued, which we can, we would get 8 third-order partial derivatives. Here would be f sub x, f sub x, y, f sub x, y, x, f sub x, y, f sub y, x, f sub y, x, y, f sub y, x, and f sub y. All the third order partial derivatives. In this class, we're going to focus mainly on just the first and second order partial derivatives. So going over an example, and this is our example from the previous page, find all the second order partial derivatives of our function 2xy plus 3x plus 4y squared. And note that on the previous page, we found that the derivatives were 2y plus 3 and 2x plus 8y. So let's find all of these. The first one we're going to find is f sub x. That is the derivative with respect to x of f sub x, xy. And I should not have that notation, sorry. The partial with respect to x of f of xy, which is just going to be the normal derivative of 2y plus 3 with respect to x. This time we're not going to break it up into each individual part. We're just going to try to think about it as a whole. Both of these terms are constants with respect to x. So that means that this whole derivative is just 0. Let's look at f of x, y. That's going to be the partial with respect to y of f sub x of xy. And that's going to be the derivative with respect to y of 2y plus 3. That's just a function of y. It's a very normal derivative. We should get a value of 2 out of that. Let's continue. Let's do the derivative, second derivative yx. So that is the partial with respect to x of f sub y of xy, which is going to be just the normal derivative with respect to x of 2x plus 8y. We know that this 8y is just a constant with respect to x. So this whole derivative should just be the derivative of 2x, which is 2. And lastly, let's do f of y, which is the partial with respect to y of f y xy, which is just the normal derivative ddy of 2x plus 8y. Noting that 2x here is a constant, so this derivative should be 8. So there are our 4 second order partial derivatives, and we're going to show on the next page that these two partial derivatives are actually the same. The f of xy, f of yx, we both got the same value, and that's not a coincidence. That's going to happen every time. So it is always the case that f of xy equals f of yx. These are our mixed partial derivatives. And that is the case if the functions are continuous. If you do have discontinuities, weird things can happen, but we're going to be mainly dealing with continuous functions in this class. So we're going to think about pretty much always f of xy equals f of yx, which means that it doesn't really matter the order that we take partial derivatives. We could take the derivative with respect to x and then y, or take the derivative with respect to y and then x. So just some closing thoughts here. We know that a function with continuous higher order partial derivatives, that means that if you can take all derivatives and you get continuous higher order partial derivatives, it is called a smooth function. And smooth functions are nice functions to deal with. And I'll draw a little picture here in a second of a smooth function. This fact of f of xy equals f of yx is important when we talk about integrals of functions of two variables, because it means that it doesn't matter which variable I'm going to be focusing on first. And this idea of the mixed partials expands to higher order partial derivatives as well. We know that f of xyx is the same thing as f of xxy. You could do different orders, doesn't really matter, they're the same thing. So let's draw, to close it out, a picture of a smooth function. And we're just going to think about a function of one variable. And we're going to look at a picture of something that is not smooth. All right, and this not smooth idea, these are continuous functions, but the derivative does not exist at those cusps and corners, right? So there's something, the derivative is not continuous everywhere. But if you have a smooth function, the derivative will exist everywhere. And this translates to functions of two variables as well. So here's like some maybe sheet or something, that's a smooth function, whereas a cone would not be smooth because of this corner right there. We're going to be thinking about smooth functions almost always in this chapter, in this course, but wanted to introduce that topic. We'll look at some examples of computing partial orders algebraically in the next video.